On a single day in 2017, a spacecraft that had already lost the use of 2 of its 4 reaction wheels, forcing NASA engineers to invent an entirely new way of operating it, just to keep it pointed steadily at the stars, recorded 10 hours of starlight from an ordinary, unremarkable K-dwarf star called HD 137010. Buried inside that 10-hour window was a signal, so faint, so shallow that it represented a change in brightness of roughly 0.02%. An amount of dimming that had never before been successfully used to identify an Earth-sized planet from a single transit alone. Nobody caught it in 2017. The data simply sat in NASA's public archive for years, one dataset among millions, waiting. Then, in January of 2026, a team of astronomers led by Alexander Venner went back through that old retired spacecraft's archive and found it. Not a new observation, not a new mission. A planet quietly hiding in nearly decade-old data that nobody had ever previously identified with confidence, orbiting near the outer edge of its star's habitable zone. This is the real story of what researchers just discovered inside Kepler's own archive data, why it required inventing a genuinely new detection technique to find it, and why one of the telescope's most quietly remarkable legacies is that it's still finding new worlds years after it stopped operating entirely. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why this specific discovery required such an unusual approach, you first have to understand exactly what the Kepler Space Telescope was built to do, and why it stopped doing it years before this planet was actually found. Kepler launched on March 7, 2009, on a mission specifically designed to answer one of the most fundamental questions in all of astronomy. How common are planets like Earth, genuinely rocky worlds, orbiting within the habitable zones of stars similar to our own Sun? Its method was elegant in its simplicity. Kepler stared continuously at a single fixed patch of sky containing roughly 150,000 stars, watching for the tiny periodic dimming that occurs when a planet passes directly in front of its host star from our specific vantage point on Earth, a technique called the transit method. Over its original 4-year primary mission, Kepler transformed exoplanet science almost single-handedly, confirming thousands of new worlds and establishing, for the first time, with real statistical confidence, that planets are common throughout our galaxy, not rare exceptions. But in 2013, partway through that primary mission, Kepler suffered a serious mechanical failure. The spacecraft relied on 4 reaction wheels, spinning devices used to precisely control its orientation in space without wasting limited fuel, and it needed at least 3 functioning wheels to maintain the extraordinarily steady pointing its science required. When a second reaction wheel failed in 2013, following an earlier failure in 2012, Kepler's original mission should have effectively ended right there. Instead, NASA engineers devised a genuinely creative workaround, using the gentle, consistent pressure of sunlight itself, a phenomenon called solar radiation pressure, combined with Kepler's 2 remaining reaction wheels to keep the spacecraft stable enough to continue collecting useful data. This extended mission, using this clever balancing technique, became known as K2, and it allowed Kepler to keep observing different patches of sky in a series of sequential observing campaigns, each lasting roughly 80 days, until the spacecraft finally ran out of the fuel needed to maintain even this compromised pointing solution and was formally retired by NASA in October 2018. One of those observing campaigns, K2 Campaign 15, ran during the summer of 2017, and it's within that specific dataset that the star HD 137010 was observed, a Sun-like K-dwarf with an apparent visual magnitude of 10, 1 meaning it's bright enough to be a genuinely favorable target for follow-up study, but not so bright that it had already been exhaustively studied by every other survey. During that observing campaign, Kepler's photometer recorded a single transit event lasting approximately 10 hours, during which the star's measured brightness dipped by just 225 parts per million, an extraordinarily shallow signal, roughly equivalent to detecting a change in brightness smaller than 250 thousandths of the star's total light output. Here's why that specific number matters so much, and why this discovery required a genuinely novel approach, rather than simply reprocessing old data with existing tools. The standard, well-established way astronomers confirm a transiting exoplanet is by observing multiple repeated transits, watching the same dimming pattern happen, again and again at consistent, predictable intervals as the planet completes multiple orbits. That repetition is what gives researchers statistical confidence that they're looking at a genuine planet rather than random noise, instrumental error, or some other astrophysical false alarm. The problem with HD 113710b, the designation the team eventually gave this candidate planet, is that K2's observing campaigns only lasted around 80 days each, and if this planet's orbital period is longer than that window, which the data strongly suggests it is, Kepler would have only ever caught a single transit, with no way to observe a second one to confirm the pattern using traditional methods. As the research team's own published paper states directly, the transit method remains one of our best tools for detecting potentially habitable Earth-like exoplanets, and in principle, given sufficiently high photometric precision, cool Earth-sized planets orbiting sun-like stars could theoretically be identified from a single transit event alone. But the paper is equally direct in noting that this specific feat, confidently identifying a genuine Earth-sized planet candidate from just one observed transit, had never actually been successfully accomplished before this study. Venner and his team of collaborators, working with data that had been sitting in NASA's public archive for close to a decade, became the first to actually pull it off. Doing so required an unusually thorough, multi-layered investigative approach, precisely because a single transit event on its own is genuinely difficult to distinguish with confidence from a variety of other phenomena that can mimic the same basic signal. The research team combined their analysis of the original K2 photometry with several additional independent lines of evidence: historical imaging of the star system stretching back years, brand new follow-up imaging observations conducted specifically for this study, archival radial velocity measurements tracking any subtle gravitational wobble in the star's motion, and precise astrometric data tracking the star's position in the sky over time. Taken together, this combination of evidence allowed the team to systematically rule out the most likely alternative explanations for the signal. Things like a background eclipsing binary star system whose light happened to blend with HD 13710's own light in Kepler's imagery, or some other kind of stellar activity capable of producing a similar brief dimming pattern. The team's own published conclusion was carefully worded but genuinely confident. Their combined analysis strongly indicates that the transit event was a real astrophysical signal, that it genuinely occurred on the target star itself rather than some background contaminant, and that the most plausible explanation for everything they observed is a genuine transiting planet candidate, which they formally designated HD 13710b. The physical characteristics the team derived from that single transit event are genuinely striking. Based on the depth and duration of the transit, HD 13710b appears to have a radius of roughly 1. It grows 6 times that of Earth, making it, in the most literal sense, Earth-sized, not merely Earth-like in some loose, approximate way, but essentially matching our own planet's physical dimensions almost exactly. And in terms of its position relative to its star, the research team's own published analysis places HD 13710b specifically near the outer edge of the traditionally defined habitable zone, the range of orbital distances where a rocky planet could plausibly maintain liquid water on its surface, assuming it possesses a suitable atmosphere. The team's own supplementary analysis directly describes HD 13710b as an exceptional example of an Earth-sized planet orbiting near the outer habitable zone edge of a genuinely bright, sun-like star, a combination that makes this particular candidate stand out even among the broader, growing catalog of potentially habitable worlds astronomers have identified in recent years. It's worth being completely honest here about exactly what astronomers currently know and don't know about this planet, because that honesty is precisely what separates a credible discovery from an exaggerated one. HD 13710b remains formally a planet candidate rather than a fully confirmed planet, an important scientific distinction. The research team has been transparent about the genuine difficulty involved in fully confirming this specific discovery going forward. Because the planet was detected through only a single transit, astronomers don't yet know its precise orbital period with certainty, meaning they can't currently predict exactly when a future transit might occur in order to directly observe and confirm a second one. And attempting to confirm the planet's existence through radial velocity measurements, detecting the star's subtle gravitational wobble as an independent line of evidence, presents its own serious technical challenge. The research team directly compared this challenge to previous, extensively studied radial velocity work done on a similar star, GJ 9827, another 10th magnitude K-dwarf hosting a known system of planets. Even with more than 50 precise measurements from a top-tier spectrograph, combined with over 100 additional archival measurements, astronomers still only managed to constrain those planets' gravitational signals to an uncertainty of about 1/4 of a meter per second. Detecting the comparable signal expected from HD 13710b would likely require an even larger number of similarly high precision observations, a genuinely demanding, resource-intensive undertaking for current-generation instruments, meaning full independent confirmation of this planet candidate may take real time and dedicated follow-up observing effort to achieve. Despite that honest uncertainty, there's a broader, genuinely important story here that goes beyond the specific fate of this one planet candidate. This discovery represents real, meaningful proof of concept for an entirely new detection technique, one capable of finding Earth-sized worlds from single transit events, a category of detection that had simply never been successfully demonstrated before. And it's worth appreciating exactly where this discovery came from. Kepler stopped actively collecting new data in October 2018. This planet candidate was found in January 2026, more than 7 years after the spacecraft itself went permanently. Silent, hidden inside data that had already been sitting in a public archive, freely accessible to any researcher for nearly 9 years before anyone successfully teased this particular signal out of the noise. This isn't an isolated case either. Kepler's retired archive has continued producing genuine scientific discoveries on a surprisingly regular basis in the years since the mission officially ended. In 2020, researchers reanalyzing old Kepler data identified Kepler 1649c, an Earth-sized planet sitting within its star's habitable zone that had originally been misidentified by an automated screening algorithm and effectively overlooked until a dedicated human review caught what the software had missed. In 2025, an entirely separate research effort revisited a specific target designated KOI 134, originally flagged and then dismissed by Kepler's own automated detection pipeline as a false positive, and confirmed not only that the original signal represented a genuine planet after all, but that the system actually contains a second, previously undetected planetary sibling as well, one orbiting on a distinctly different tilted plane that had prevented it from ever producing a detectable transit signal in the first place. And in 2019, a full decade after Kepler first detected it as an unconfirmed candidate, researchers finally confirmed Kepler 1658b, one of the very first exoplanet candidates the mission ever flagged, using an entirely independent method involving sound waves propagating through the host star's interior. Taken together, this pattern reveals something genuinely remarkable about how modern astronomy actually works, a detail that rarely makes it into flashy headlines but represents real, ongoing scientific value. NASA's deliberate commitment to making its mission data permanently, freely available in public archives means that a spacecraft's scientific contribution doesn't actually end the moment its instruments go silent. Kepler stopped observing new stars in 2018, but its accumulated archive, encompassing years of extraordinarily precise photometric measurements across hundreds of thousands of stars, remains an active, ongoing source of genuine new discoveries, limited only by the ingenuity, patience, and analytical techniques of researchers willing to keep looking. As NASA's own retrospective on Kepler's legacy has put it plainly, there are still, in the agency's own words, many treasures left to be found in the Kepler data, a statement this specific discovery of HD 15710b now stands as direct current proof of. So here is where this genuinely leaves things, honestly, as of early 2026. A 10-year-old dataset gathered by a spacecraft that had already been mechanically compromised and creatively kept alive, using little more than the pressure of sunlight itself, has yielded a genuine, scientifically credible candidate for an Earth-sized planet sitting near the edge of its star's habitable zone, detected using a technique, confident single-transit identification, that had never been successfully demonstrated before this specific study. The planet's status remains, honestly, a candidate rather than a fully confirmed world, awaiting further observation to nail down its exact orbital period, and ideally, an eventual independent confirmation through additional transits or painstaking radial velocity work. But the underlying achievement here, proving that Earth-sized worlds can be reliably identified from Kepler's archive using nothing but a single, carefully analyzed transit event, opens up a genuinely new avenue for finding potentially habitable worlds hiding in plain sight, inside data that has already been sitting freely available to any researcher willing to look closely enough. If this kind of story is what you come here for, one grounded in exactly what astronomers actually found and honestly still need to confirm, hit subscribe and turn on notifications, because there's clearly a lot more hiding in this old data still waiting to be found. Drop a comment telling me whether you think HD 1137010b will eventually be confirmed as a genuine planet, and share this with someone who still thinks a retired telescope has nothing left to teach us.